Hello, my name is Antons Mislevics and today we will talk about machine learning. I want to start this story going back 20 years when in 1997 IBM Deep Blue supercomputer had beaten Garry Kasparov in a game of chess. And back then, everywhere in the press people were talking that now the era of smart machines start, because machines are so smart that they can even beat the best human beings in so intelligent game as chess. If we look back now, we can see that this was not a revolution of artificial intelligence, but it was more a revolution of computing power, of processors. And nowadays, even your mobile phone can play chess as good as Deep Blue back then. Later, in the year 2011, IBM Watson supercomputer had won people in Jeopardy game. In that game, computer was asked questions in English. He had to understand what he is asked and prepare the right answer. Last year, everywhere in social media, there was a lot of coverage for this event that computer had beaten world champion in the game of Go. The game of Go is interesting because it is considered a non-computable game. There are so many moves and so many positions that it is not possible to count all of them. What describes this game well is that when the best players are asked why in one or another situation they've performed one or another move, usually they say, I don't know, I just feel this way, I feel this game this way. And it's interesting that even in this level of feelings, machines can be better than humans. Earlier this year, two separate research projects, Liberatus and DeepStack, managed to beat humans in the game of poker. This is interesting because poker is imperfect information game. You do not know what cards your opponents have, and also there is this element of bluffing. So this is really interesting results for artificial intelligence. Over the last years, we've seen significant progress in image recognition scenarios. Nowadays, machines can recognize road signs better than humans, and in classical postman test, where you need to read handwritten digits from the envelope, zip code from the envelope, machines perform approximately as good as humans. There is a slight margin, but practically maybe it's not so important. Among the people who do image recognition, there is a large competition, world championship, or maybe even Olympic Games. It happens once every year, it's called ImageNet, and there are quite a lot of objects, a lot of categories of objects, and what's interesting that teams need to recognize not only what they see on the image, but also where this object is located. In the year 2015, two interesting things have happened. First, Microsoft research team had won. It was not a surprise because Microsoft research team historically is very strong in image recognition scenarios. Another thing is that for the first time in the history, machine had surpassed human level performance in this test. Last years, we start getting a feeling that machines actually can not only detect objects on images, but they can understand what they see. Here are some examples. In the left column, you can see where machine tried to describe what it sees on the image, and it did it pretty well. Like here, a person riding a motorcycle on a dirt road, or a herd of elephants walking across a dry field. Very precise. On the right column, you see some examples where machine was not so good, like a yellow school bus parked in a parking lot. We will talk about it a bit later. What it allows us to do is to identify different objects on images and also analyze how these objects are related together. And here are some examples. For example, machine can say that this is an airplane, airplane is flying, airplane has windows, it has engines. And on the next image, for example, we see an elephant, and machine can say that elephant is standing, this is a shadow of the elephant, and a man in a red shirt is sitting on an elephant. So it's pretty interesting results. It also allows us to perform logical operations on images. For example, here you see image of a car minus blue plus yellow, and you get other cars. With colors, it may be simple. And that's why I like these examples more. You have airplane, you say minus flying plus sailing, and you get boats. If you want to play more with image recognition, I would encourage you to go to clarify.com. They are one of the leaders in image recognition scenarios. And for example, recently I went to their website, I uploaded this image of Riga city, and here you see the labels, what it could give to this image, what machine sees on this image.
I'm Priscilla, one of the test drivers on the Google self-driving car project. Our team is responsible for keeping the cars and other people safe while on the road, and for providing feedback on how they perform in the real world. A big part of our job is to go out into the world and uncover all the potential scenarios that a car might encounter. Then we help the engineers teach the car how to best navigate each one. Here are some examples of situations that we regularly encounter on the streets of Mountain View, California. We've taught the vehicle to recognize and navigate through construction zones. Our sensors spot the orange signs and cones early to alert the car of the lane blockage ahead, and we can change lanes safely. You'll also notice the vehicle typically moves to keep a safe distance away from large obstacles, like this truck stopped on the side of the road. Now we're approaching a railroad crossing, which requires special care. Notice the red fence and railroad sign that appears to the computer as we approach the intersection. This means that we'll wait until the tracks are clear of other vehicles before proceeding. Our cars treat cyclists as a special category of moving object. Watch in this example, when the cyclist holds up his arm, our software detects the hand signal and predicts his movement into our lane. The car knows to continue yielding to the cyclist passing by, even when he changes his mind, multiple times. We still have more work to do, but it's fun to see how many situations we can now handle smoothly and naturally. See you on the road.
Looks pretty impressive, right? And if you are riding a bicycle, you should feel much more safe now, waiting for when self-driving cars will arrive to our streets. Machines get creative. Here are some examples. First, in the first experiment, you can take your favorite photo and your favorite painting, give it to machine, and machine will reproduce this photo as it was painted by your favorite artist. In the next Rembrandt experiment, scientists tried to predict what would be the next painting, what Rembrandt would come up with if he would manage to do. And here is this painting, and also you see a reference to a link where you can go and find much more information about this experiment. Pretty interesting stuff. Machines can complete images. You show an image with some part cropped out, and machine can find what needs to be inserted in this part so the image is complete. And finally, machines are used to enhance images. You give an image in bad resolution, and machine may find what pixels need to be added so the image is much sharper. You can see it here. If you don't see it on your screen, I encourage you to go to the link on the slide, and you will be able to zoom it in and you will see the results much better. It's not only about images. In recent years, we see significant progress in text-to-speech and voice recognition scenarios. First, last year, Google had announced that now they have the technology that can speak like this.
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser.
Sounds pretty interesting, and for me, for example, I do not hear this metallic background sound, what you usually would expect from the machine. This sounds pretty much like human. And a bit later, Microsoft had announced that now we have the technology that can listen to conversations of groups and can recognize individual words with the same level of precision as professional transcribers do. What else machines can do? Machines compose music. The music you hear now in the background was composed by machine. Machines can generate handwriting. Here are some examples. The first line is written by human, and then machine tried to emulate the handwriting of this person. And the next thing is machine translation. If you're using online translators, perhaps you've you could feel that over the last years the quality of online translation, of machine translation, had changed dramatically. Why it happened? Because the whole approach to translation had changed. If previously we were trying to take individual words and word pairs in some language and translate it to another language, what we do now, we try to extract the meaning from words and word pairs. From it we construct the meaning of the entire sentence, and then we go all the way back and try to deconstruct this meaning into this sentence and words in another language. What you see now, machine is learning how to play a computer game. It's part of Google DeepMind experiment. DeepMind team is a team that managed to beat world champion in Go game. Here, what's interesting about this experiment is that machine is getting an image, what you see now on the screen. It doesn't know what it needs to do in this game. What it knows that this is an image and I have a joystick and I can press some buttons on this joystick, but machine does not know what each button on the joystick do. It only gets the signal when it earns the point or loses the point. In 2 hours, this machine managed to learn playing like this. And in 2 more hours, it have found an interesting tactics how it can win this game pretty quickly. It may look like games, but the real goal of this experiment is to build a general purpose artificial intelligence. Imagine that you can show some situation to machine and you can just tell the machine what it can do in this environment, and machine will learn by itself how to behave here. Machine learning is happening not only in research laboratories, it's actually transforming businesses. Perhaps you come from different industries, so I will not give you examples from specific industries, but if you look around, if you look at your partners, at your competitors, perhaps you've heard that they use machine learning in one or another way. And it happens not only in Silicon Valley or in some research laboratory cities. It happens worldwide, and it happens in your country as well. Now, let's take a look at how machine learning works. Machine learning is not a black magic. It's well-structured, well-organized process. Here you can see the machine learning process. It all starts from data. And the first step, you need to analyze and pre-process this data. You need to clean it out from anomaly values. You need to understand how to merge different data sources together, how to aggregate this data. You need to clean some empty data, for example, and then you get clean prepared data. This is a phase where machine learning experts spend most of their time. Then you start training the models. This, I believe, is the most exciting stage, where you try to train different models and see which of these algorithms work better for a specific problem. And then you select one, or usually you select few best performing models, and you deploy them. You deploy them as a web service, and you can start using it in your business solution. Machine learning is not a black magic that can solve any problem what you have. It can answer few very specific questions. Here you can see the questions, and based on the question you are asking, you select the algorithm what you will be using to solve this problem. Let's take a look at the first two, regression and classification. I want to give you the feeling how these two work. Regression helps you to answer the question, how much or how many. Here is a typical example. You have some village. In this village you have many houses. You know prices for most of them, but you don't know for few, for example. And you want to train machine learning algorithm so it can predict and tell you the price of these houses for which you do not know the price. Consider that you have the data set like this. You have the price and you have the size of the house in square feet. What you can do, you can put it on a plot. So here each dot represents one sample from your data set, what you have. And in this data set, this size of the house is input variable. This is what you get and what you know. And the price is output variable. So this is something what you want to predict. What you can do now, you can draw the line through this data set. This line is called hypothesis, or the model what you are building. And you will be using this line to predict future values. How you do it? When you have a new sample for which you know the size but you do not know the price, you just look at this chart, you put this size of the house what you have, you see where this point will be on the line, and then you see what the price for this house will be. How you can measure how good this model is? Usually you measure how far the line goes from all the points in your data set. And this is, the closer the line will go to the points in the data set, the better your model is. How you can improve your model? You can try different algorithm or different lines, so you can find the line that will go closer to the points, to the dots in your data set. Another thing what you can do, you can get more data, because if you're getting more data, more rows in this data set, you can better see the pattern of this data, how this data looks. Or you can get more variables, so your data set gets wider, because most probably the price of the house depends not only on the size, but on other features as well. And this is why recently people are talking about big data so much in the context of number of samples what we have and in the context of how many information each sample contains. And this is it. This is regression. This is how it works. Now let's take a look at classification. Classification helps you to answer the question which category or which class. Typical example looks like this. Imagine that you are an insurance company and you are selling car insurance, and what you know about your customers is how many years they are driving and what is their age. These are your input variables, and as an output variable you want to predict a risk class, first or second. Same as before, you can plot these points, and then what you are searching for in this case is you are searching for classify or hypothesis or model what you are building, a line that will separate these two classes. So basically the line that will smoothly separate yellow dots and blue dots in our sample, because yellow dots are one class and blue dots are another class. And so in this case, when you get a new sample, you can see where this dot will be, and then you will see on which side of the line this dot will be, and based on it you may decide on what is the right class for this sample. Of course, it may happen that your new sample will be precisely on the line, and then machine has a problem. If you have more than two classes, you can use one versus rest approach, where you train separate classifier for every class, and then when you have a new sample, you compare it to every classifier and select the one that returns highest confidence score. Recently, I believe you've heard a lot about neural networks and deep neural networks, and that's why I wanted to give you an example so you have a feeling of what are neural networks and how they work. Here is an example. You can go and play with this environment and playground tensorflow.org. I want you to look at this right area of this slide. What you see here are yellow and blue dots, same as before. And what we are looking for, we want to train our neural network so it can build a line that perfectly separates these two classes together. Now I start the neural network learning process. You can see that network learns and it tries to find the line that will separate these two classes. And what's good about neural networks is that neural networks can build a function, a line of any complexity. You can see neural network completed learning. Here is a line that separates these two classes perfectly, and if you would want to build this classifier with mathematical methods, with a mathematical function, it would be a pretty complex function, right? Now, let's talk about how to implement machine learning in your project. This is the machine learning process we were discussing before, and I want to remind you that it all starts from data. You need to collect the data. Without the data, you cannot do machine learning. Then you need to ask very specific machine learning question. Remember, here is a list of these typical questions, and you need to understand how to formulate your problem the way so it will be, so you can ask machine one of these questions. Then you need to know that there are some typical machine learning scenarios in which machine learning works pretty well, and they are not industry specific. They work in different industries. Here are these examples, and it would be good if you look at these examples and as a first machine learning problem you select one of these problems, because these are time-proven easy to implement machine learning scenarios. Then you need to know that implementing machine learning is not only building the model, but you need to ensure the entire process, starting from the data, what you get, maybe collect from some sensors, then you need to store this data somewhere, then you need to build machine learning models, and then you need to publish these models and integrate them with your systems, or maybe generate some visual reports from them. And this is why software vendors as Microsoft offer you packages, like package solutions for machine learning. In Microsoft, it is called Cortana Intelligence Suite Services, and it aggregates different Azure services that allow you to get from data to real actions. If we talk about implementing machine learning model itself, then I would say that there are three ways how you can do it: easy, medium, and hard. Now we will go through them one by one, and I will show you how they are different. So the easy way is to use something what is called cognitive services. Then you can integrate this machine learning model with your solution using web service. How it works? Cognitive services are machine learning models that are trained and maintained by some vendor. Here is an example of Microsoft Cognitive Services. Good examples are emotion and face APIs, for example, what we have. Emotion Cognitive Service works the way so you can submit an image to this service. The machine learning algorithm will identify all faces, what it sees in this image, and will identify what emotions it can see on this image. And it will give you back the JSON with all information what it could extract from this image. What's good about it that you do not need to train your machine learning model, you do not need to maintain it. It is all done by some vendor, as Microsoft in this case. Microsoft has more cognitive services than this, so I encourage you to go to Microsoft Cognitive Services if you're interested and look through all the services which are there and see how they can be used in your project, because this is the easiest way how to integrate machine learning in your project. You just need to call a web service and you get the response. Next, more complex level to implement machine learning in your project is to use Azure Machine Learning Graphical User Interface. Then you can publish developed model and integrate it with your solution using web services. Here is how it works. Azure Machine Learning Studio is an environment that allows you to build the entire machine learning process using the graphical user interface. So you drag and drag blocks, you connect them together, and this way you can select data sources, you can decide how to pre-process this data, aggregate data sources together, train your models, evaluate the models, do all this stuff. This is a screenshot of how it looks. If you want to go this way, I encourage you to go to Cortana Intelligence Gallery. This is a place where we publish a lot of examples around machine learning. For example, you can see different solutions for different industries. You can open them up, see what data sources are we using, how we are pre-processing them, what machine learning algorithms are we using, and how it all works. And also we have so-called solution templates. These are end-to-end solutions. You can pick one and you can deploy it in your Azure environment. And remember that Cortana Intelligence Suite, it had many services in Azure environment, and these solution templates will configure all these needed services the right way in your Azure subscription. Finally, we have Azure Machine Learning Algorithm Cheat Sheet. This is a good source of information for you to familiarize yourself with different algorithms which are there in machine learning world and which of these algorithms may solve your specific problem. Now, let's take a look at the hard way to implement machine learning in your project. In this scenario, you can take Azure Virtual Machine with GPU, deploy any machine learning libraries what you like on it, Theano, Torch, TensorFlow, Caffe, CNTK, any of them, pick the one you like, and then you can start writing the code to define your models and train your models. Technically it looks like this. You write the code, you run it in a console, and you can also monitor resource usage on your machine. You can see how it works. So it's pretty low-level stuff, and it is the hardest way to implement machine learning. One more thing what you need to consider when you are selecting the right way to implement machine learning in your project from this easy, medium, hard is the cost component, because as you go lower from easy to hard, the cost increases as well. This is related to both implementation cost and operational cost. Now, let's take a look at where all this is going and how the future of machine learning looks like. Let's start by looking at what brought us to where we are now. Why machine learning is developing so rapidly in recent years? There are three components to it. Perhaps you've heard about these three already. First, we have data. So we have something on which we can train our machine learning models. Then we have algorithms. Because of the fact that in recent years, deep neural networks, the same algorithm, is used in different domains, like voice recognition, image recognition, we can see that algorithms in this area are improving as well. Finally, there is computing power. When talking about computing power, people usually think about cloud, that cloud vendors as Microsoft or Amazon are giving you unlimited resources on which you can execute your machine learning algorithm. You can train these machine learning algorithms. The fact is that one thing is still missing, and this is GPUs, graphical cards. Because of the people who liked playing computer games, we now have very powerful graphical cards, GPUs. And it turns out that neural networks specifically are computed very effectively on these GPUs. Here is a good example to you. In the year 2011-2012, Google was building their machine learning data center that was called Google Brain. They put 1,000 servers in it. Each of them had 2 CPUs. And it took them around $5 million to implement it. 2 years later, in the year 2014, you could compute neural networks of the same complexity on just 3 NVIDIA graphical cards. These are quite expensive and powerful graphical cards, but still there are just 3 of them, and the cost of this solution would be just $12,000, much less. And now it was back in the year 2014, and it continues developing on the same pace. In the beginning of this presentation, you could see some pretty impressive examples of what machines can do already today, but there is some critics to it. First important thing, what scientists are saying, that neural networks can be fooled. And here are some examples where convolutional neural network was trained to recognize objects in images, and this research shows that it is possible to generate synthetic images, and when these synthetic images are given to machine will not see the difference from the real image. Here are more examples, like you can see a starfish or a baseball or electric guitar. For humans it does not look like anything similar to these objects, but machine does not see the difference. Remember, I was showing you examples where machine was asked to generate description for the image, what it sees on the image. We were seeing some good examples and some bad examples, and what is interesting about it is that if machine gets it wrong, it may get it wrong completely. Here are some of such examples. A man riding a motorcycle on a beach, a young boy is holding a baseball bat, or a horse is standing in the middle of a road. Another thing is that if I show the image like this to you and I ask what will happen next, you will definitely say this bottle will fall. Machine does not understand it. It will say that, oh, I see a table or a chair and I see a bottle, but it does not understand how the world works. It does not understand that this bottle will fall. And so if we look in the future, we think that machines need to learn and understand how our world works, so they need to get some level of common sense. They need to learn a very large amount of background knowledge about our world, and most probably it will not be through supervised learning where we are giving some examples to machines and machines are learning from them, but we need to give them the way to manipulate the world and see how the world responds. And that's why scientists believe that the future is about unsupervised learning. That's all, and now a few things I want you to take away from this session. First, imagine what machine learning can do for your project. Describe how machine learning works and what machine learning is to your stakeholders. From my experience, if business stakeholders understand that machine learning is not a black magic, regression is just a line, classification is just a line, and this is how it works, they get much more supportive and they'll support machine learning initiatives in your organization. Start small, look for quick machine learning wins. In order to do it, it's better to pick some classical machine learning problem as your first exercise and try to implement it in your organization. It is important to define what precision is really required for your solution. Maybe you do not need 90–95% precision, maybe 80% will give economical effect already. Choose the most appropriate end-to-end machine learning implementation approach so you can do it quickly, and focus on pushing these models in production. You cannot evaluate how good this model is unless it starts working with real data in production environment. Next, create data culture in your organization. Machine learning is based on data, so you need to invest in people who know how to manage data, and you need to invest in data in your organization. And you need to improve data quality in your organization. And finally, when you're talking about machine learning with your customers or with your stakeholders, do not sell it as just another cool thing. Try to calculate return of investment, economical effect of implementing machine learning models, and sell it this way, sell business value. That's all, thank you very much, and good luck implementing machine learning.